Go. In a pharmaceutical plant, copper pipe with inner diameter of 20 millimeters and a wall thickness of 2.5 mils is used for carrying liquid oxygen to a storage tank. The liquid oxygen flowing in the pipe has an average temperature of -200 and a convection heat transfer coefficient of 120. The copper pipe is insulated with a 3.5 centimeter, 75 centimeter thick insulation around the copper pipe and the conditions surrounding the ambient air temperature of 20 Celsius and a combined heat transfer coefficient of 20. Okay, so stressing on what we're just talking about in theory, right? So this convective heat transfer coefficient that you're given, okay, this guy is the H over here, which is related to the interaction between the air and the insulator. Okay, so it's a very precise number, and you're given it now, and later we're going to have to find that number. Okay, we are to estimate the temperatures at the outer surface of the insulation and at the interface of the copper pipe and the insulator. We can assume thermal contact resistance to be negligible. So what do we have here? We have O2 here on the center. Let's do a little color for it. We have O2, liquid oxygen, and we have liquid oxygen at -200. So -200 Celsius over here. And we have air on the outside, and that's at 20. So we have air on the outside at 20, like so. So before I do anything else, I can be sure of the direction in which heat will be flowing through this pipe, right? We have a little pipe. Oops, have a little pipe. And there's oxygen inside, it's flowing somewhere, and we know there will be energy on this direction here, right? Going in or out through the surface area of that pipe. And what we know is it's going to go from hot to cold every single time. We have no doubt about that. It's not something it's debatable, right? So we know that Q is going inside the oxygen tank. Now, let me go ahead and open this other window that I have here. Now, what do we have? What are the resistances that we have? Well, we're going to have a copper pipe, and that's this layer here, right? The copper pipe, and it has a certain thickness to it. And we'll also have an insulator. So insulator over there, which is going to try to stop that heat from going in. Okay, before we even start, we can have a certain idea, right? When we try to figure out what's the resistance of these guys, we would expect the copper pipe, knowing copper is a good thermal conductor, especially in relationship to a insulator, that the insulator would have a thermal resistance that's way higher than the copper pipe, right? Just by looking at our Ks, our conductivities, we have 400 versus 0.005. So just that on its own should give us a pretty different thermal resistance. But on top of that, we also have a 2.5 millimeter thickness copper versus a 37.5 mils thickness insulator, right? So we can already expect some values to come out of that. First thing we do on these problems, as I told you guys last week, is we find our radiuses, because this is where most people go wrong. This is where most people go wrong, finding radius, as silly as that might sound. And when we're finding the radiuses we have, I'm going to go ahead and call this guy A, B, and C. So I'm going to do the inner layer will be my A, the copper one will be my B, the insulator will be my C, and my air will be my D. Okay, so I'm going to use those letters to make our lives easier. And then let's go ahead and do, this is going to be my R1, this will be my R2, and my R3. And if you guys are doing this with me, let's see if you don't do any mistakes, okay? Because I remember last week we had some problems when grabbing our radiuses. So make sure you're really comfortable with this. The inner diameter is 20 mils. So our first radius will be the 20 mils divided by 2, right? So that's going to be 10 mils, okay? Or 10 to the minus 2 meters, right? Now our second one will be the R1, right? Plus the thickness of the copper pipe, which is 2.5. So R1 plus 2.5, which will be 12.5 mils. And last but not least, we have R3, which is our R2 plus the thickness of the insulator, which is 37.5 mils. So this guy turns out to be 50 mils. Okay, so just getting those guys in order before you guys actually start thinking about thermal resistances and conductions and convections will sure be a bonus when you're solving these, especially in a midterm or an exam, okay? Now, what are the resistances that we have? Well,
Pablo,
go. Yep.
Is it 3.75 or 37.5 for the insulator?
3.75 centimeters. Same thing as 37.5
centimeters, 37.5 millimeters. Yep.
Yep.
Perfect.
Cool.
All good.
Cool. All right. So what do we have here? Let's do a little electric circuit analogy. Okay. So the first thing we need to look is, okay, we're going from the outside to the inside. That's where our red arrow is telling us, right? So if heat is going from the outside to the inside, can it go from the outside to the inside without crossing all the layers, or can it go around some of the layers? Is there any parallel system in this? So we take our pencil, we start over here, and we try to make our way inside. You can try to do whatever you want. You won't be able to avoid all these layers, right? So we need to go through all of them, which means that this is a system that's in series, and because it's in series, we can construct a little circuit that's in series, and we're going to have minus 200 on one side. And then we know we're going to have a first resistance, and this first resistance is due to convection, right? The convection resistance that O2 creates. And why do I know it's convection? Because O2 is a fluid. If it's a fluid, it's always convection. If it's a solid, it's always conduction, okay? Rule of thumb. Then we have the copper. So our copper is going to be another resistance, and that's going to be a conductive one. And then we're going to have the resistance due to the insulator, and that will be a conductive one again. And finally, we have air, and that air, when energy is being transferred from the air to the insulator, will have another convective one. And on this outside here, we have 20 Celsius. So this would be RA, RB, RC, RD. And we can go ahead and do an extra step just for the sake of learning, which is convection, conduction, conduction, and convection, right? And once this is set up, this is pretty much like, in terms of our thinking around this problem, is pretty much it, because now what we can do is we can find what is our heat transfer, and we can use that to our advantage, because check out what we need to find. We need to estimate the temperature on the outer surface of the insulator. So let's put that down. So this will be right here, right? Outer surface of the insulator, just there. And we also need to find the temperature on the interface between the copper pipe and the insulator. So right, let's change colors to blue, right there. That is what we're looking for. Okay, so one way to think of this is, my pen allows me to get rid of these guys here. What we can do is put little extra dots in there. Those dots are the temperature as it decreases or increases as we go, okay? And we know that Q will be going from the outside to the inside, so like so. That is our Q there. So there's very, very important information that we know beforehand, and this is very trivial, but at the same time, I know how some of you guys get this wrong, right? So we know that it's going from the right to the left. So therefore, we know that temperature, let's give some names. Let's give them some names. Let's call this guy. Temperature 1 will be smaller than 20 and greater than minus 200. Temperature 2 will be greater than 200 and smaller than temperature 1. And temperature 3 will be greater than 200 and smaller than temperature 2. We know that, right? We know there's a distribution, there's a temperature distribution that goes like so. So on one hand, on one end here, we're going to have 20, and on the other end, this is pretty negative. On the other end here, we're going to have minus 200. So whatever temperatures we have in between will be in between these two temperatures. Okay, and you're going to see why this is going to come into play in just a second. So we're looking for the outside between the outside and the insulator. So we're looking for this T1 here. That's one of the things we're looking for. This guy here is one of the things we're looking for. The other one is between the copper and the insulator. So T2, let's make that blue to be consistent with my blue X that I drew up before. These are the two temperatures we are looking for. So what we can do is we can find one Q, and we know that Q is going to be the same Q throughout the whole thing. That's what the analogy of the electric circuit tells us. Once we have that Q, we can use that Q to calculate any delta T, right? Because check out what would happen. If I would like to find this delta T here, right? I know that this delta T equals always my Q times my R, but in this case here, it will be RD, right? Specifically RD. So in other words, this is T 20 minus T1. That has to equal the Q times RD. So that's one option for us to solve for T1. Another option, which would be just as valid, would be to do minus 200 over there and T1 over here. So what would that tell us? It will tell us that delta T equals Q and R, just like before. But what is this R? Well, that's going to be RA plus RB plus RC, right? So my delta T will be Q times RA plus RB plus RC, right? And what is that delta T? And watch out, because this is where a lot of you guys go wrong. Which one is greater? T2 has to be greater than minus 200, right? So it's going to be T2 minus 200 equals Q of RA, RB, RC. So what we're going to do to solve this question is we're going to first find all the resistances. When we have all the resistances, we're going to find an equivalent resistance that is the equivalent for all the four of them. When we have that, we're going to find what is the Q that is going through all these resistances, because they're all in series. And then finally, we're going to use that Q to find the delta T that we're looking for and find the temperature we're looking for. All right, so let's get to work. I'm going to delete. I'll just leave this here, I guess. Insightful. Okay, so we can start with our RA, just to keep the letters going. Start with our RA, and our RA is a convective. So whenever it's convective, we can do RA. Whenever it's convective, we're going to do 1 over HA, right? In this case, 1 over the H for the oxygen is 120. And the area for the oxygen is the area in contact over here, right? So this area over here. So the area in which O2 and the copper are in contact. And note how this is important. Note how this is important for you guys to understand, because it's the resistance on the interaction between fluid and solid. Is that supposed to be T2 minus T1? Where was that? This one just here? No, because check out what I did. I did the delta T from this point to this point here. Oops, I erased something in my way. Yeah, so I'm doing from the 200 to the T1. Oh, yeah, okay, yeah, perfect. Sorry, man. Sorry, 100% correct. Yes, thank you for that, 100%. That will be T1, yes. Cool. All right, so we can go back to where we're talking about the area, right? So it's the area, the interface between O2 and the copper. So that area there is going to be the radius 1 times 2 pi r, which is radius 1, times the length of this copper wire, which is this guy here, right, L, which we don't have. So this guy is 2 pi r1 times L. And we go back to that same old problem that is, okay, what are we going to do? Are we going to do L equals 1? Or are we just going to keep that L in the loop and just take it as we go? It's really up to you guys, whatever you find easier. Plugging in the number, so let's do 1 over 120, 2 pi, and then this is 10 to the minus 2, okay, in L. So this will be 0.13 Kelvin per watt if we're assuming it to be 1, or Kelvin meter per watt if we are not. So if we're carrying our L there. Okay, so we're going to still have an L component down here. Okay, whatever rocks your boat, really. RB is a conductive resistance, and if it's a conductive resistance, oh, you guys won't prefer to do L1? Okay, fair enough. Okay, just go with the masses. Let's go with the masses. So we're going to put our R star here, and we're going to say always remembering that the only reason why we can do this is because we know Q is proportional, linearly proportional to L, right? So our conduction for a cylinder, right, it's going to be that XKA, and then remember that the X is going to become the radius, and then when we integrate all the things, it will become natural log of R2 over R1 divided by 2 pi KL. We're assuming L to be 1. K is the conductivity for copper. We have all those data, so we can just go ahead and do 12.5 divided by 10 millimeters. I'm doing all in millimeters because same units will neglect each other. Then we have 400 conductivity for copper, and then 2 pi and 1 for our length. And this guy is 8.9 times 10 to the minus 5. So indeed tiny, right? Indeed tiny. Next one is RC, and RC is also conductive, and the conduction is on the insulator. So natural log of R3 over R2 divided by 2 pi KL. So this will be the 50 divided by the 12.5, which is dividing 2 pi, 0.05, the conductivity for the insulator, and 1, which is our length. And this guy turns out to be, what do I get, 4.41. Okay, and check out the difference between the two, right? 5 orders of magnitude. So indeed, like we would expect, the insulator has way more thermal resistance than the copper pipe does, right? Last but not least, we have RD, and we know RD is due to the interaction between the air and the insulator. So therefore, RD is a convective one, and because it's a convective one, it will be 1 over HA. This time, our H is different. Our H is 20, and our area is also different, right? Because it's going to be 2 pi RL, just like before. That didn't change, but our R is now the radius that is related to the interaction between the air and the insulator. So that will be our R3 in this case here. So our R3 on the bottom just there. And we have all the data that we need, right? 1 over 22 pi. That will be 50 times 10 to the minus 3. And the reason why I'm converting is because this fella here is watts per meter, right? Watts per Kelvin meter. And we also have L, which is 1 meter. There you go. And this turns out to be 0.16. Now, interestingly enough, this will be 1,000. So that's 1,000 times 10 to the minus 3. So that will be 1 over 2 pi, right? The whole math there becomes 1 over 2 pi, which is 0.16. Kelvin per watts. Always remembering that we used L equals 1. Okay, so now we have all the resistances. We can do that equivalent system, and our equivalent system is going to look something like this. And we're going to have 20 on one side and minus 200 on the other side. And we're going to have only one single resistance, which is going to be the sum of all of them. That's going to have a Q going through it. And the sum of all these guys here, if we sum them up, it's pretty much only accounting for the insulator and then a little gain from the convective. Where's my math? Okay, so that is 4.7, right? 4.7, that's the sum of all of them. And if we do our Q equals delta T over the sum of all the R's, that will be the 20 minus the minus 200 divided by 4.7. And this can be Kelvin or watts. This will be Kelvin or watts, and this will be 46.8 watts. Now, something to be aware of, okay? Something to be aware of. We are assuming 1 meter length, right? So 1 meter length. So if we were to carry our units with us, we would have, don't forget, we would have a meter over here. So let's do a different color for that because I'm going to erase it in a bit. So we would have a meter over there. Yeah, and then our kelvins would go away, and we would be left with watts per meter, right? So it would be watts per meter of length. And before I would go on your assignments, a lot of you guys were putting the final answer per unit area or per meters of length without really thinking, right? Because this doesn't happen all the time. Only happens when you assume stuff that you're not pretty sure. So on your problem, you had a 4x5 wall, so you weren't really assuming any areas. Right? I was nice to you guys. I didn't take you off any marks, but be aware of why you're doing the things you're doing. So this is 46.8 watts per meter of length. So let me remove that M there because we didn't carry that with us the whole way. Okay, and what we can do is do a little arrow to remind ourselves why that guy comes to be. That's because we assumed a length of 1. Cool, so now we know you can think that we know the current, right? It will be the equivalent of electric current that's going through that system, and we can find out the temperatures that we're looking for. So there's, like I said, there's more than one way to find this. We can do the short way, which is only having one resistance there, which is probably what we're going to do because that's easier. Or we can do the long way and sum all the R, A, B, and C. And then to find the next one, again, we would have more options. So we could have, the option of going from 200 to, I went too far. From 200 to T2, that will be one option. Or we can do from T1 to T2, which is a shortcut. Okay, so let's find our T1 first. So finding T1, so T1. We know our delta T will be, and I wonder if I should do that close to, I'll probably do this closer because it makes more sense, at least for you guys to watch this if we do it close to where we're doing it. Okay, so now we can plug in these values here. We know this is 46.8. Yeah, and those are watts per meters, right? Those are watts per meters, 46.8 watts per meters of length. And we're multiplying this by RD, which is 0.16 Kelvin meter length over watts. Yeah. So our watts and watts go away. Our meters in this case don't really matter because they would go away regardless of whether it's 1, 2, or 3. And we're left with the difference over here to be whatever that is. I didn't really calculate that because I did the whole thing straight off. So let's do it quickly. 46.8 times 0.16. That's 7, about 7.5, right? Just about 7.5 Kelvin or Celsius. Okay, so that means that our delta T, which is 20 minus T1, equals about 7.5 Kelvin or Celsius. But note that this guy here is in Celsius, right? So you cannot use Kelvin anymore when we apply the difference there, right? So that means that my T1 will be 20 minus 7.5 Celsius, which equals 12.5 Celsius-ish, right? Ish. All right, so we know that much. Should we be using RC to find between T2 and T1? We should, but we're finding T1. If we're going to find T2, we're going to be using RC, or we can use the other way around. It's up to you. So that's precisely what we're about to do. So now we need to find T2, right? We need to find T2. We have a couple of options. Let me get rid of what we had before here. Actually, go back to this afterwards. So now we have a couple of options because now we know this guy here is 12.5 Celsius. So we want to find T2. So what can we do? Well, we can do RC, right? From the delta T from T2 to T1 is related to the resistance RC. Or we can do that guy there, right? We have options. And as a matter of fact, I'm going to do the long way now just to show you that it's going to work just like the other one. So let's keep this like it as is. What I'm going to do is I'm going to remove this guy here, and I'm going to do from 200 to T2. Okay, so from 200 to T2, we have our A and RB between. So this guy, we don't need this guy anymore. We don't need this guy anymore. This is T2. Okay, so T2 minus 200 equals the Q that we found before and the sum of the two resistances, RA and RB, right? And if you guys recall, RB and RA and RB are not very big, right? Remember what RA was? It was 0.13, and RB was in for copper, which is 10 to the minus 5 something. Remember what it was on the dot, but it's 10 to the minus 5. And what I would like to do is create some space here for myself. Let's see if I can do that. So we can zoom out, just grab this chunk. Have this chunk here and send it downwards. Cool. So I have some space there. So now all we can do is, okay, so that means that my T2 minus 200, so plus 200, equals my, what else do we have there? My 46.8 watts per meter length times the sum of 0.16 and 10 to the minus, what was that? Where is it? Oh, it's the bottom. 8.9 times 10 to the minus 5, yeah, which was pretty much nothing, right? .9. This is Kelvin meters per watt, so we're going to be left with Kelvin or meters. So that means that my T2 will be about negative 193.9 Celsius. Okay, so there's heaps of ways to do this, right? There's heaps of ways to find these two temperatures here. You can, if you want to study some more, you can just do it with other ways. You can go from the 200 all the way. You can go from the 20 all the time. You can mix and match these, and these should all work. Exactly the same answer by the end of it. What we can do is do a little analysis before we sign off of this question, which is check out what happens with the temperature from the inside, the oxygen, which is at minus 200, to the interface until we hit the insulation, right? It's pretty much the same temperature. There's really no thermal resistance happening there. Right? We have minus 200 in the center here. There's running out of colors. Minus 200 in the center here, and we have minus 193 over here, right? Minus 193 over here. And then we just found out this guy here is about 12.5. So check out, the insulator is doing its job, right? It's doing its thing. It's keeping this this energy barrier, let's call it, this delta T barrier between the minus 193 to the 12.5, okay? So the insulator is doing a thing like we would expect, right? And then the convective barrier is also small. As we know, there's a 20 Celsius going on over here on this side. So from our analysis, it makes sense. The values that we have make sense. They're consistent with what we would expect, right? The other last thing is that if we were to find this guy here, what is this guy here that we would like? If we were to find this guy here, T3, which is this guy right there, right? We would have something between minus 200 and minus 193, right? That has to be the case. Is there ever a time you have to use a long way or always have a choice? You always have the choice. You always have the choice. No, you always have the choice. Doesn't matter. The long way is useful when if you're doing an exam. The long way is useful to check your answer, right? So if you do the short way or the long way, you should get exactly the same thing, right? So if we were to repeat this question and do it the long way, we should get also 12.5 Celsius as our answer. So it's a way for you to check your work if you want to, but you always have the choice. Any other questions?